Hi, good afternoon, and welcome to episode 3 of the Stanford AIMI Center's NextGen Tech Talks series. My name is Joanna Kim, and I serve as the Executive Director of the Stanford Center for AI in Medicine and Imaging, also known as the AIMI Center. Our mission is to accelerate the development, validation, and dissemination of AI methods that advance health responsibly for everyone, everywhere. We aim to be a vibrant community at the forefront of AI research, education, implementation, and policy. Before we get started today, I have a few quick announcements. First, the AIMI Center will be having our flagship annual meeting, the AIMI Symposium, on May 15th. This all-day event will highlight the latest work in academia and industry for AI in medicine. It's free and open to all, and registration for virtual participation is still open. So if you're interested in attending, we would be delighted to have you join us, and a link is here for more information. Also, our next Tech Talk will be on Tuesday, June 25th, with Dr. Jessica Miga, who's a cardiologist here at Stanford Healthcare and also the co-founder of Verily, which was originally known as Google Life Sciences. The link to register for the next Tech Talk is also here as well. And now I'll pass the Zoom mic to Dr. Ala Youssef, who is a researcher here at Stanford AIMI and co-director of the AIMI High School programs. Thank you so much for listening to the announcements, and I hope you are all inspired and excited about the future of medicine through today's Tech Talk. Thank you.
Thank you so much, Johanna, and welcome everyone. Few quick reminders. So reminders that please put in your questions into the Q&A function, and please use appropriate language, and do not. It's better to use the Q&A function to upvote questions, as well as respect behavioral. Any participants behaving inappropriately would disrupting the event or violating these guidelines will be removed from the webinar. If you have any specific questions or concerns, please feel free to reach out at the AIMI Center. And we have the delight today of having two incredible speakers. Today, the speakers are two Stanford faculties, Dr. Akshay Chaudhari. He's the Assistant Professor of Radiology and Associate Director of the Stanford AIMI Center at the Stanford School of Medicine, and Dr. Sergios. Gatidis. He's an associate professor and clinical radiologist at the Stanford School of Medicine. And we have two amazing moderators, Sarah Penn and Arv Wattle. Sarah is a former AIMI intern, and Arv is a former AIMI intern and now a Stanford undergraduate student. So welcome, and I will hand it off to Dr. Chaudhari to get us started.
Hi, everyone. My name is Akshay. I'm an assistant professor in radiology and biomedical data science here at Stanford. I'm delighted to be here. I think there's many of you online in this webinar, so hopefully excited to have a nice conversation with everyone. And maybe for a quick introduction, I just wanted to give folks a little bit of a high-level background on some of the things that we do in our research lab and how I got to where I am, because I imagine there might be a lot of questions about understanding career trajectories and trying to understand, how is it that's easiest potentially to have a large-scale impact in healthcare. So way back when, I attended undergraduate university at UC San Diego, so not that far from here, studying bioengineering. I actually went to undergrad thinking that I wanted to become an MD, a medical doctor, and to be able to increase the likelihoods of me getting into med school, I started doing academic research. But while I was doing academic research, I realized that I really loved doing research, being able to ask big picture questions where there's no structure, there's no right answer. And I just really enjoyed the creative thinking process where you could think about different hypotheses and really conduct experiments that you could scientifically justify. So I really fell in love with this paradigm of doing research, which is what inspired me to be able to go to graduate school directly after my undergrad. During my time as an undergrad, I also did a couple of academic internships at a major biotechnology company called Genentech. I spent 2 summers over there, and it was really interesting that I could compare and contrast both of these different roles. And all of this made me realize that the contribution that I wanted to have in the world was to be able to build new technology to help patients. I didn't necessarily want to become an MD and interface on a day-to-day basis with patients because I thought that was maybe a little bit emotionally too hard for me. But I wanted to be on the back end, and I wanted to create enabling technology to help everyone who's in need. So I came to grad school here at Stanford. I was admitted into the bioengineering PhD program, where a majority of the research that I did really focused on improving medical imaging acquisition. So I was working a lot with new medical imaging technologies and trying to ask questions like, how do we make our current existing technologies faster? How can we get more information from the same amount of time? And how do we make some of these technologies safer? So I was very excited about utilizing my engineering background and to be able to bring a really nice signal processing perspective to medical imaging so that we can continue doing the things that we're good at already, but to be able to improve the state of access and the quality of the medical imaging tools that exist. So I wrapped up my PhD in 2017, and I really wasn't sure about what I wanted to do afterwards. I wasn't sure if I wanted to continue in an academic position or if I wanted to go work at a company. So what I tried to do was to be able to consult for a few local startups on the side just to be able to better understand what life in industry is like. What is it like to be able to build a product as opposed to doing research? What is it like to be talking to different customers at different times and learning market needs? And that was a very valuable experience, but it made me realize that my true passion really lied in doing research and being able to ask big picture questions that are maybe 5, 10 years out the line, and really being able to create a research program to ask and address these big picture questions. So that's kind of my trajectory, how I got here. I've been at Stanford since 2012, which is when I started my PhD program. But I started my role as an assistant professor in 2020, October of 2020, which was a great time to start a new role at a university. And ever since then, I lead the machine intelligence for medical imaging research lab in the Department of Radiology. And the focus here, as the name implies, really focuses on building new machine learning based solutions to help address medical imaging related challenges. Our lab consists of 15 or so researchers that are focusing on a whole host of different research activities, all the way from trying to acquire the highest quality images, to trying to come up with new image analysis methods, to using language models to better understand the inputs and outputs of radiology text, and more recently, being able to build multimodal models that can learn using both imaging data as well as language data. So how do we build these vision language models? So hopefully that was a very quick overview of my background. I'm delighted to be here, and I'm happy to chat about anything that folks would find helpful. But with that, I will now turn the floor over to our second guest, Sergios Gatidis, who's a new radiologist here at Stanford. So Sergios, please, floor is yours.
Thank you, Akshay. Thanks, everyone. It's great to be here. I look forward to our discussions today, and I'd like to share a few thoughts about my past and also share some slides to illustrate what I've done in the past and how I came to be here at Stanford. So I grew up in Germany, southern Germany, and I decided to study medicine at some point. And I decided to study medicine because I thought, you learn about everything if you study medicine, because medicine needs everything. You need to learn about biology, biochemistry, about physics. There's nothing that you cannot learn if you do medicine, and later on you can still decide what you find interesting. But when I went into medical school, I quickly realized that there's one field that's quite separate, or back then at least, was quite separated from medicine, and this was computer science and mathematics. Of course, there were some statistical tools that were used in medicine, but overall there was a noticeable difference in distance between the medical field, the biochemical field, the life sciences, and the mathematical department at the University of Tübingen where I was. So I thought I'd like to understand both of these fields, and I started also studying mathematics in parallel to my studies in the medical school, and I was swimming back and forth between these fields. And back then I did not really have a plan what to do with this combination. I was focusing on medicine, and the mathematical part was more of a hobby. Also, I thought initially that this is what radiology looks like. Basically, you acquire radiographs. That's a radiograph of the chest. And I was not really interested initially in medical imaging until later during my studies, I came to see these images or similar images. And this is what radiology looks like today. You can acquire unbelievable detail of medical disease, depict medical disease, show human anatomy, function, without being invasive. Can look inside the human body without being invasive. And I still think that's unbelievable. It's hard to believe sometimes. Of course, I got used to it over the years, but it's a phenomenal achievement of technology and science. So I decided to become a radiologist. And after medical school, I went into radiology, and my specialization is in hybrid imaging, which is a technique that looks at different combinations of imaging modalities. And in parallel, because all these images are digital, I decided to have my diploma thesis, which is something like a master thesis in mathematics in an applied field in 2012. And this was in radiology. And back then, the task was to separate different tissue components within the body. And there was no deep learning available to me. So it took me almost a year to figure out how to separate adipose tissue compartments from lean tissue compartments within the body on whole body MRI scans. And there were all these ancient techniques that we used, histogram analysis and active contours, and it was really, really difficult, and the results were not so great. So this was a difficult time for medical image analysis, and it seemed like we would never make progress in this field, or very, very slow progress. But still, I was starting to have a better interaction between the medical field and radiology and the computer science field. And then in 2012, and it's something that feels like ancient history now, but this was a great moment also for medical image analysis. These papers came out in 2015, the UNED paper, that really showed what you can do with deep learning in the image analysis field. And suddenly everything became possible. So we've been working on automated detection of tumor lesions, on removal of motion artifacts from medical images, or improvement of image quality in PET imaging. So there are so many applications that became possible suddenly, overnight, basically, within a few years. And the field exploded. So at this point, I thought, at least I have something like a submarine traveling between the fields. And I was able to work with many colleagues from different institutions, which also was very important for my career development. And then in 2023, I came to Stanford. And the reason is because here, we are building a bridge with at least 4 lanes in each direction between medicine and AI and machine learning. And this is a very exciting place to be. And this is a place where I think the future applications of AI in medicine and medical imaging will be built. So I'm very excited to be here to serve as a radiologist, but also as a scientist in the field of medical image analysis. So just quickly, where are we at the moment? There are many applications, AI applications, that are already applied to the medical field, and almost all of them, most of them are related to radiology, and even those who are not are mostly related to imaging. But still, there are some questions that are open, many questions actually. One question that I'm interested in is pediatric imaging. And as you can see here, only very few applications are available for children in the AI field. So one question that I have is, how can we improve the performance of medical AI in pediatric patients that doesn't work well out of the box? Here, it's an example of organ segmentation, but with some tweaks and some technical developments, we can make this also accessible to children. Yeah, I hope that was already an introduction that's helpful to you, and I'm very happy and look forward to discuss details with you and talk about all the questions that you might have.
Thank you very much, Dr. Gatidis, Dr. Chaudhari. Actually, it was very insightful to hear both of your talks. Dr. Chaudhari first, about how you fell in love with research, went to grad school, started building technology and bioengineering to make medical imaging faster. And Dr. Gatidis, to how you grew up in Germany, decided to study medicine, and how you were uninterested by medical imaging, but then you started specializing in multimodality images and related projects. But me and Sarah will be we'll be asking a few questions from now. So my name is Arv Wattal. I'm a freshman student here at Stanford, studying computer science and electrical engineering. And actually in high school, I took part in AIMI's first summer internship program, where my team and I created an AI pipeline to identify and box various tubes in chest X-rays. And currently, I'm actually pursuing medical technology development here at Stanford, and I'm creating an AI-powered robot arm to assist the elderly and disabled.
Hi, I'm Sarah Pan. I'm a senior at Phillips Academy in Andover, Massachusetts. In the summer before my junior year, I met Arv through working with him during AIMI's first internship program. Since then, I've returned as a student lead in the program and have worked on various projects outside of AIMI. On behalf of not just me and Arv, but the entire team of student moderators doing NextGen Talks, we're just more than excited to kick off the Q&A session. So yeah, one question I have for you, Dr. Chaudhari, is multimodal models have kind of been really hot recently. And I was wondering where you could see them kind of fitting into AI and radiology in the future.
Yeah, that's a really good question, Sarah. So I think maybe before I answer where I see them fitting in, maybe I'll talk about some of the challenges involved in actually scaling to multimodal models for healthcare broadly. So right now, if we look at the general machine learning domain, we'll see that a majority of the research exists with 2D multimodal data. So we might have a particular image, and we're trying to caption what the content of that image might be. Or maybe vice versa, if we provide some sort of text prompt, we can generate what image corresponds to that text prompt. So that could be your DALL-E or Stable Diffusion type models. We have a very good mechanistic understanding of how to train these models, generally where they work and generally where they don't work. But I think it's actually really challenging to be able to scale some of this to 3D data sets. So for example, going from a single image to video generation can be pretty challenging because now you have to generate multiple hundreds of frames. So for example, when OpenAI's Sora model was previewed, everyone was very excited how we now have the capabilities to solve some of these problems. We don't necessarily know the workings of that model because it hasn't been publicly shared, but that same example can apply for a lot of medical imaging data. So I'll give, for example, a challenge of some of the data sets we're working with right now. So if we're trying to image the chest, a chest radiograph or a chest X-ray is very common. It's a single 2D image, but then a lot of times you can also get some chest CT scans that can have 300 to 500 of slices in the same volume. So how do we scale dimensionality to these higher data sets, both on the imaging side as well as on the text side? Normally, for most 2D models, we have a short sentence that describes whatever is in that image. But now, when we're working with some chest CT data, for example, we have a big paragraph or a long number of tokens that really describes that. So I think there are some fundamental challenges in how to actually build some of these systems. But then every good challenge is an opportunity, if you ask me. So if we are able to build some of these models, I think we can just ask the same types of questions we've always been asking, but we have much better tools at our disposal. Now, a lot of times, places like Stanford, we're fortunate to have expert radiologists like Sergios, but some of these multimodal models could be helpful in resource-limited settings where we might not have, let's say, a thoracic radiologist specialty. We might have a general radiologist. So how can we upskill a certain segment of the population? How can we actually reduce the data needs for solving very specific tasks? So if we're able to build some of these self-supervised models with multimodal data, then I might need fewer patients to build a secondary model on top of that to understand what will happen to a patient in the future. So I think the questions we can ask remain the same. These questions all revolve around how can we improve patient outcomes, but now we just have a much better set of technologies to answer those questions. I'm sure Sergios will probably have a lot of comments on that too.
Yeah, so I agree with what Akshay said, and I think in general, it's really hard as a radiologist to estimate what machines will be able to do in the future, because on the one hand, we tend to highly value what we are able to do. So we would like to remain experts in our field and wouldn't like to be replaced by machines or by algorithms. But on the other hand, I think it's very exciting to see how research groups like Akshay's group are working on tools that can really work and help us solve medical problems that we don't want to do. For example, repetitive tasks or quantification of image content, something that can take a lot of time. And I think these would be the first applications that we would look into. And later, I can see how more and more complex tasks will be solved by these tools. And it's extremely important to include not only imaging data, but as Akshay already pointed out, text data and other clinical data that we have at our disposal in order to solve these problems.
Thank you, Dr. Chaudhari and Dr. Gatidis. That was very insightful. And on that note that you just mentioned about kind of these different kinds of applications with medical imaging, why hasn't there been as much imaging and AI research for certain populations like pediatric imaging, for example?
Right. So I think it's mostly a question of numbers and focus. So one thing we need to understand is that you need a very, very large amount of training data for most of these applications. And it's much easier to collect these data from adult populations where certain diseases are very frequent and easily accessible and are imaged frequently. So we have lower numbers of pediatric patients that receive imaging examinations. That's one thing. But the other and related aspect is that, of course, the general interest and maybe also commercial interest in pediatric applications is slightly lower compared to certain adult blockbuster applications where you can have tools that solve problems for millions of patients in contrast to thousands of patients maybe on the pediatric side. But I think the focus is shifting, and this also has to do with the models that are developed, which basically do not really care or will not really care in the future whether it's a pediatric patient or an adult patient, but will likely have a more global view on medical imaging. And I think that's very exciting.
That makes perfect sense, actually. But on a similar note, then, is the approach for research with AI imaging different for adults versus children, like overall?
Yeah, and sorry to interject, but kind of on that, in terms of more specific methodology, without getting into something too technical, what would sort of constitute a good foundation model for medicine? Would it be something that understands both, adult data and children's data, or what would that sort of look like?
Actually, I think that's something that you can answer better than I can.
Yeah, do you want to take the pediatric part first?
Yeah, I'm glad to take it first. So I think there's no substantial difference between the technical tools that we need to build applications for children or for adults. I think there's one challenge in children, which is that there's some diseases that are so rare that we cannot use the traditional approach where we just collect thousands of examples in order to train a model in a supervised manner. So there are questions of whether we can do few-shot learning, which means learn by only having a few examples of a disease. And I think this relates very much to being able to build large foundation models that have a very good understanding of imaging and medicine in general that can then be fine-tuned on a small number of examples. And that's something that Akshay is working on at the moment.
Yeah, and it's a very good question about foundation models. And I think this kind of touches on Shripriya's question too about where we see the future of AI research going. And I think we're definitely seeing this path of these large-scale foundation models. But these days, I feel like it's also good to be able to separate the term from a scientific standpoint and a marketing standpoint too. Every model is being categorized as a foundation model. And if every model is a foundation model, then there's no foundation model at the end of the day. But I think fundamentally, when I think about these foundation models, they need to have capabilities that work across modalities. So for example, if we imagine a patient presenting to a hospital, and maybe it's for, let's say, cancer screening, Maybe the patient might have some mammograms that are associated with her. So we have some imaging data. Maybe if these mammograms are suspicious, the patient might go to biopsy. So there might be some pathology data associated with too. Maybe there might be some sort of genomics assay being performed to understand what type of cancer might be at play. And all this time, maybe the patient is getting a lot of different blood tests, a lot of different labs being performed. So we have all these heterogeneous data sources that exist for a given patient. If you ask me, the ideal foundation model will allow you to integrate all these disparate modalities into a singular model. That's challenging, right? Because right now, the way a lot of our healthcare system works is we generally have a specific focus and specific specialization. We have experts in radiology, we have experts in pathology, we have experts across different fields. How do we really integrate all this data? And how do we make insights looking at the holistic patient perspective rather than looking at singular slices? I feel like that's where I really see a lot of future research going. And I always find this quote compelling when I think about where I want research to be in the future. People tend to overestimate what we can perform in the short term, and we underestimate what we can perform in the long term. So thinking about characterizing an entire patient's journey into a singular model so we can draw the best insights is what I think are the best qualities a foundation model can have.
That makes perfect sense, Dr. Chaudhari. Thank you. And you did mention that there are like different specializations within med that people tend to specialize in. So for a lot of the high schoolers watching, so for someone who wants to go into a career at the intersection of AI and med or AI and radiology, AI and medical imaging, anything like that, what kind of educational path might you recommend for them?
So I think there's no correct or wrong way to do this, as long as you're interested and you follow the path that you find most interesting. And we need experts in all domains in order to move forward. So we need experts, very good experts in the medical field, who know what they're working on, who know the disease, who know how to approach a patient. But we also need experts who are really good at developing new techniques in machine learning that can solve a specific problem that we have in medicine. But if you ask me what we need, more than we have maybe, is people who understand both worlds and who can translate between the two domains and explain medical problems to the AI community or identify techniques within AI that can solve specific medical problems that exist. So I think this is a field that offers a lot of opportunities, and in order to get into this field, it's of course helpful to have some medical knowledge, biomedical knowledge, and also some basic knowledge in computer science and mathematics.
Yeah, I fully echo what Sergios mentioned. I think it's really important to have a very strong technical background, but then there's many different mechanisms that could allow you to gain this technical background. You could be a math major, you could be an engineering major, but as long as you have really good insights about how do we think about data, how do we build some computational tools to be able to manage and analyze data sets, I think that's a very fundamental key. And then knowing what is the best application area to work in. Now, if we want to be an expert in AI and healthcare, it's unlikely that we're the real experts in both of those. But what really matters on top of that is knowing what you're good at and knowing what you're not good at. So for example, I know very little about clinical radiology. That's why it's always a pleasure working with clinical radiologist experts like Sergios to fill the gaps in knowledge that we have. Because I think at the end of the day, especially when we want to aggregate broad data sets and broad fields together, then we need to be able to learn from experts in each of those domains. You need to have your own strength that's coming in, but then you need to be able to defer to the other expertise that your peers may have.
And that's also something that I'd like to emphasize. You cannot do this alone. That's a field where you really need big teams with diverse expertise in all these fields in order to make true progress.
Yeah, so I noticed that both of you mentioned that there's a sort of like trade-off between being maybe an expert in one thing and not another, and being able to have those collaborative skills that allow you to sort of work with people and experts across different domains and fields. And so in terms of another binary, how do you kind of approach balancing technical innovation and clinical applicability in your work? And especially when developing AI tools that ideally would be used in hospital settings or like real world settings?
Yeah, happy to start with that too. I think it's probably going to be very use case specific, and the answer might change on different settings. But whenever I'm faced with a new question where I need to develop a new set of skills, I always first ask, do I know someone with those set of skills? Because sometimes it might be faster for me to go talk to that person or go have a coffee with that person and to be able to learn so that I can save my time trying to add a skill set that no one else has, rather than replicating something that someone else may have already. Because at any given time, there's 100 different things that you could work on. There's only really time to do 5 of those things really well. So the more picky you can be about what is the best way to use your time so that our broader knowledge as a community is increasing, rather than replicating the same expertise, that's at least my lens for figuring out how to be time efficient.
Yeah, and regarding your question on whether to focus on technical development or clinical application and how to select between those, I think there's always a risk involved. When I look back at, what we've been doing 10 years ago, or maybe we were working for a year on something that could be solved in a month nowadays. AI is a field that develops so quickly, so rapidly, that it's really hard to predict what we will be able to do next year. But at some point, you want, and especially as a radiologist, as a clinician, you want to apply the tools that are available. So I think a good trade-off is to apply tools whenever you can expect reasonable success with the tools that are available for a relevant clinical problem. And if that's the case, then you can take the risk and say, okay, maybe there will be a new technical solution in a few years, but a lot of the work that you can do in applications is dependent of that. You can collect data, you can design a study, you can validate or build a validation pipeline. And this can be used again for new techniques that will be out there next year or in 2 years. So it's a difficult question to answer, but I think the main aspect is that it should be a relevant clinical problem and should be solvable in a reasonable way with the tools that are available.
Those are very good points. And Dr. Gatidis, towards the end, you mentioned that I guess AI is a field that's applications are broadening so rapidly, especially within the medical field these days. And sort of related to that, now that you guys are doing a lot of novel work and probably you require a lot of training data, how do you deal with what challenges do you encounter with kind of gathering that training data related to creating those novel models?
Yeah, so training data, of course, is everything in machine learning. We learn on data. That's the essence. And there are several challenges. One challenge is, of course, an ethical challenge in medicine related to data privacy and security. So we do not want to expose our patient data to the public. We also don't want to build models that memorize details of individual patients. So there are many aspects of using data that we need to take care of when we use clinical data. On the other hand, I think every patient has the right to contribute their data and to enable progress that will be helpful for them and for other patients in the future. So I think it's an ethical balance, but overall, there's more benefits than dangers in using medical data for machine learning if done correctly with the appropriate precautions. And the other challenge, I would think, is a technical and engineering challenge. It's really, really not easy to scale your compute, your storage, your frameworks to deal with, thousands of terabytes of data. And that's something that I'm not sure whether it has been solved technically in general. I know Akshay is working heavily on that, but it's a real engineering challenge beyond the scientific aspect.
And I think the other comment that I want to be able to make regarding data is we should be careful in thinking about where the data comes from and what sort of additional information is actually embedded in these data sets. So for example, I'm a professor at Stanford. It is easy for me to be able to work with data that's acquired at Stanford Hospital. But then because of that, I need to be cognizant about, well, what are the characteristics of the data sets of patients who come to Stanford? Are they representative of the national population or the international population we want to be able to benefit? Do we see a difference in disease prevalence? Do we see a difference in the types of demographics of patients? So at the end of the day, that's the data that I have access to, but there's variations in that particular patient population versus the broader population. So the data can carry a lot of biases in them, and it's up to the algorithm developer to really try to understand as well as they can what are the plausible use cases and what is your data not actually good for. Even if you had a large scale, are there specific segments of the population or specific diseases or specific medical imaging devices that your model will consistently fail on just because you don't necessarily have that slice of training data represented at your institution?
So you guys kind of talked about how, data can be a sort of finicky thing in terms of, being able to attribute it to, the patient and privacy concerns. But, recently there's been a huge advent in generative AI, as I'm sure we all know. And you can probably generate synthetic data. I think someone asked a question about FAM data. Correct me if I'm wrong. I'm assuming this means synthetic data. But there also seems to be a sort of hot debate on whether synthetic data works or not. So I was wondering if you guys could tell us about a few pros and cons of generating and using synthetic data, and maybe a personal take or two on whether it actually works.
Well, I think that's something that we've been debating with Akshay for quite some while. And I think synthetic data are an extremely intriguing field and idea. And I personally am not sure how they work, but it seems, I think they do work. I think there are some applications where it's obvious that they can be helpful, for example, for training of radiologists and residents and trainees. You can just generate data that look real and they show a specific pathology, so a human can learn about medicine on synthetic data, right? So that's something that's very much obvious, I think. And you could build public repositories, for example, of data that are synthetic, that do not belong to a specific patient, so you can circumvent the data privacy issue. But I think the real question is, do they have a role in training machine learning models? And that's something I think that Akshay can discuss much better.
Yeah, I think it's a really good question. And I don't think there is a clear answer that we as a community know. I think there's a lot of research that's pretty active in the space. And this is something that we're exploring too, because we know that the data set size for most machine learning models is a limitation. Why don't we just build a generative model to generate synthetic data? Well, the first challenge is it's hard to build that generative model in the first place, because our tasks are challenging because the data set is complicated. Now we're trying to build a generative model to create this complicated data. So it's a little bit of a catch-22 situation. So there's some scenarios where you can actually characterize your training data relatively well and build these generative models. And I think it really depends on what you do with these generated synthetic images. I think it's my perspective that we shouldn't be using them directly in any downstream models, but potentially we can create a large pool of synthetic data that we can use for some self-supervised pre-training of an algorithm, so that our algorithm generally knows, what does a brain MR look like? What does a head CT look like? What does a chest CT look like? That model doesn't have to be perfect, but as long as it's better than nothing, that's a good start. And then we can take that particular model and then we can fine tune it on some real data, so that we have very specific outcomes that we care about. I think that approach is pretty popular across a variety of domains. We're exploring that and we've seen some positive results in radiology. I've seen a lot of papers that do that for natural image classification. There have been synthetic data approaches that are being used for language models. I think a lot of new language models that are coming out have actually been trained on the outputs of prior language models too. So being able to characterize what the quality of your synthetic data is very essential, so that you can say this is good or this is bad. And then really knowing what is the use case you want to use that synthetic data in can also be a useful consideration. But I'm very optimistic. I think it'll just be up to us as a community to figure out what are some best practices we can develop so that we don't actually embed some challenges about synthetic data generation into our final models.
Thank you for your detailed answer. That was very insightful. And one more thing, going off of that, is kind of how you both approach the balance between technical innovation and clinical applicability of your work, especially when developing sort of AI models for healthcare professionals and related applications.
Well, I think at the moment, the big opportunity is in working on the technical aspect, because the gradient, so to say, the increasing capabilities year over year is so great, so rapid, that it makes sense to understand how these methods work before rushing into application. So I think the effort that we spend and our time that we spend is much better invested in understanding the technical workflows, the data collection process, the pipelines, the validation pipelines, before rushing into very specific applications, unless there is an application that is extremely relevant, yields high clinical returns and great clinical support for physicians that we can solve already.
I have a very similar perspective to Sergio, so I won't repeat another verbose answer.
Okay, so I think that's about all the time we have. So I'd like to extend a thank you to our two speakers, Dr. Chaudhari and Dr. Gatidis, for their talks tonight. It was really, truly insightful. And yeah, so I think one major takeaway for me, at least, was that there's sort of a lot of, I guess, collaboration, I think, between like different modes of thinking and types of disciplines within AI and medicine. That's something I'll probably carry with me as I think about future in AI and medicine. But yeah.
Thank you, Sarah and Ara, for being great moderators and for asking very hard questions.
Yeah, thank you so much.
Have a good night. Bye-bye.